Okay, so the strong nuclear force is also the strongest of all of these. The next strongest is one that we should be familiar with. It's the electromagnetic force. Okay, so if we look at the electromagnetic force, we know is, you'll think about it as in like the electromagnetic spectrum, and so it's to do with things like light, and so but actually the electro and magnetic were originally two separate forces. We originally thought it was the electric force and the magnetic force until Maxwell brought things together and said these things have to work at the same time. So it has to be electromagnetic. You can't have an electric field without a magnetic field, and vice versa. Okay, so what this does, because it's electro, it actually acts on charges. Okay, so it acts on charged particles. So anything that's charged. So for example, if we went back to the strong nuclear graph that looked like this, where this was 0.53 FR, and we said up here, as soon as we go past 0.5 backwards, it becomes repulsive. This is where, this region is where the electromagnetic force takes over. Okay, because these two things are proton and proton, and then when they come together, we know they're going to repel each other. Or if it was maybe a proton and electron, they're going to attract each other, and so the electromagnetic force acts on charged particles. Okay, we also have to know its range, like we said before with the other one. Its range is actually infinite. Okay, so this electromagnetic force you can never escape. Okay, you will look at this again in A2 electric fields, but essentially you can think of it as if you wanted to look at light. Okay, so we know electromagnetic is light, so let's just put in here what the exchange particle is first, and it will make a little bit more sense. So the exchange particle of the electromagnetic force is an electromagnetic wave, so it's what we call a photon, which has the symbol of a gamma, Greek letter gamma, and it's photons we'll look at in the quantum section. It's basically if instead of looking at light as a wave, because this is particle physics, we prefer to look at it as a particle because it makes things a little bit easier, but also it does technically act as a particle in certain situations and waves in others. And this is kind of the concept of wave particle duality, but that's another video. Photons, the range of photons is pretty far. You can look at a star that's billions of light years away and you can still see light from it. That means the photon doesn't cease to exist along the way. It doesn't decay into anything. It exists for an infinite range as far as we can tell. And so this means that the range of the electromagnetic force also has to be infinite. And in A2 electric fields, you'll see that this has some pretty strange effects. It means that if an electron wants to truly leave the atom and become ionized, it has to travel an infinite distance away from the nucleus, which is quite a weird thing to think about. But again, we'll go through that in when we get to the A2 videos. So we know that it acts on charged particles, we know its range is infinite, and we know its exchange particle is a photon. And this is the second strongest force that we have. Okay, they won't ask you as much about the electromagnetic force. They're kind of interested in the strong force purely because it's kind of weird and strange, but they won't ask you too much about electromagnetic. The third one that we're going to look at is called the weak nuclear force. So we had the strong nuclear force. Now let's look at the weak nuclear force. And the weak nuclear force is a little bit different. So the weak nuclear force acts on literally everything. Okay, there's no particle that doesn't feel the weak nuclear force, but its job primarily is decays. Okay, whenever you see a question that says this is beta decay, or this is kaon decay, or meson decay, or muon decay, or anything that involves a decay, it's always the weak nuclear force. Okay, so it's a very common question, they'll say this is a type of decay, state the interaction that occurs, and this interaction is the weak nuclear interaction. Okay, so the weak nuclear force acts on everything. Its range is kind of a tricky one, because there are 3 different exchange particles. So the exchange particles, we have 3 different ones, and they are W plus, W minus, and Z naught. Okay, so these are the 3 exchange particles that happen to be in the weak nuclear force. They have different charges because they are used to balance out the charge in an overall interaction. That we're going to look at when we look at the types of interactions. We don't have to worry about which charge we'd use too much. Just know that these are massive particles. By massive, I don't mean they're literally huge. I mean they contain mass. But they have different masses depending on which one they are. And so each one will have a different range. And so for the A-level spec, we don't have to worry about what the range of each of them are. We just have to know that the weak nuclear force is primarily responsible for decays, and anything else about it is just going to come down to you mostly drawing out the decays using Feynman diagrams, or being able to explain things about this. Another common thing is that we'll look over this again. Strangeness is not conserved in a weak nuclear interaction. Okay, now this is because in all of the other interactions, when a particle interaction happens, when we have some sort of reaction, everything has to be conserved. We know this from looking at things like conservation of energy, or conservation of momentum, or conservation of charge. These are what we call quantum numbers. Okay, and all of these quantum numbers, we've already looked at some in the examples of baryon numbers, lepton numbers, strangeness. These are quantum numbers that must be conserved in all interactions. But strangeness, again, because it's strange, isn't actually conserved when we have decay. So if you ever have a decay and they ask you what is not conserved in this interaction, your answer is going to be strangeness. Okay, and finally, the last fundamental force is gravity. Now, gravity is the weakest of all the forces, although it seems pretty strong. It's actually incredibly weak, especially on a particle scale where we're looking at incredibly small masses, because gravity, we know, acts on anything that's got mass. So, for example, it will act on a proton, but it's not going to act on a neutrino, for example, or a gluon, or even a photon, which are also massless. Okay, so they act on mass. Their range is also infinite. Okay, and this is something you'll go through in A2 gravitational fields again and look at. And it's just the idea that if you truly want to escape a field, electric fields and gravitational fields have very similar properties, and so if you want to escape an electric field, you have to go an infinite distance away. So if you want to escape a gravitational field, you also have to travel an infinite distance away. Now, the last thing that we have to know about gravity is its exchange particle. Now, the exchange particle for gravity, because it's so weak, is very difficult to detect, because it would require very high amounts of energy for us to detect something that small. And so the exchange particle for gravity is purely theoretical. Okay, we haven't actually observed this particle yet. We just assumed that because we've observed all of the other particles for those interactions, we have to have an exchange particle for gravity, and we call that a graviton. but we simply haven't got high enough energy apparatus to be able to actually detect this yet. Hopefully in a few years we might get closer to it, but it is just an incredibly difficult thing to detect. Okay, so let's draw a summary table now. So let's just pull everything together into one table so we can compare all of the different forces and look at everything all in one. So let's make a table of the force. Then we're going to look at the exchange particle. Then we're going to look at the range and what it acts on. Okay. Now the force, I'm going to list them in the order that we've gone through them. This is also the order of their strength. So the strong force, or the strong nuclear force, is the strongest. The exchange particle, we said, were gluons for between quarks. But then we said that we could also have pions for between nucleons. Put that in brackets as well. Its range, we said, was between 0.5 to 3 femtometers, and it acts on quarks. Okay, so anything that contains quarks will be acted on by the strong force. Okay, then the next one we looked at was electromagnetic. So the electromagnetic force, we said its exchange particle is a photon. So let me just draw a separation line between these two. Its exchange particle is a photon, its range is infinite, and it acts on charged particles. Okay, and then we said the next strongest was the weak nuclear force. The weak nuclear force has a exchange particle. We have 3 of them. We have W+, W-, and Z0. Its range, we said we didn't have to worry about, so I'm just going to put an NA in here because it's kind of, like we said, it's different for each of the exchange particles, and it's different depending on the energy of them, so we don't really talk about them too much at A level. And then the weak nuclear force acts on everything. And then last, we said the weakest of all the fundamental forces is gravity, and its exchange particle is the purely theoretical one. It's a graviton, and its range is also infinite, just like the electromagnetic force, and it acts on anything with mass. Okay, so as soon as we have anything that contains mass, it means that gravity is going to act on it. Given that we're looking in particle physics at things that are ridiculously small, the gravitational force is ridiculously weak. But that doesn't mean that it's not there, it just means it's not very powerful, so it's not going to be the fundamental interaction that takes place. So this is fundamental forces. Hopefully this will make sense, and thank you for watching.